Hi, ever wondered if you could dethrone Google? From the title of this video you might think I did something illegal like Google dorking. But no, what I did was totally legal. You could have done it all by yourself and I encourage you to do so. Well, recently I have built a search engine that's faster, simpler and, dare I say, more reliable than Google itself. And the best part? I used Google's own programming language to do that. Let me show you how I did it. Back in the early 2000s, Google dominated the search engine industry by using simple yet reliable algorithms to rank pages based on relevance. But over time, Google got bloated with AI, ads, and tracking, slowing it down. So I thought, what if I built a search engine that does just one thing well, finding the most relevant results fast? Alright, before we get into how my search engine beats Google, we need to talk about TF-IDF, the algorithm that made Google so good in the first place and that I am using in my own search engine. And don't worry, I'll explain it simply. TF-IDF is this magical machine, called an algorithm, into which you input the documents you want to search and a query. Inside of it, a bunch of maths happens, and the most relevant results are spat out. But how does that happen? Say we have 3 documents, as shown on the screen right now. These documents are very simple, but yet are enough to be searchable. Term frequency, abbreviated as TF, measures how often a word appears in a document, relative to its length. Say we are searching for the word fox. Now, as you can see, it appears in every document here, exactly once to be exact. But it's not just the count that matters, but the frequency. To calculate TF, you need to divide the number of occurrences by the number of words. TF tells us fox is most important in document 3, relative to its length. But that's only half the story. Inverse document frequency, IDF, penalizes words that appear everywhere. The formula is IDF equals logarithm of number of total documents divided by number of documents containing the word. There are 3 documents in our example. The word fox appears in all of them. That's 3. IDF thus equals logarithm of 3 divided by 3, which is 1, and logarithm of 1 is 0. But if we look at the word canines, that appears in just one document, IDF of it is logarithm of 3 divided by 1, which is 3, and the logarithm of 3, assuming it's base 10, is 1.098 something something something. Since the word fox is everywhere, its IDF is 0. It's not a good differentiator. But the word canines is rare, so its IDF is high. Well, at least relatively speaking. Now we multiply TF and IDF to get, wait for it, TF-IDF. You can see all the maths in the table on the screen right now. Notice, the word fox gets a TF-IDF of 0 in all the documents, thus it's too common to be useful. But the word canines only scores in doc 3, making it a strong signal for the document. If we were to search for canines, only the 3rd document would show up. But if we searched for fox, every document would show up, as the word fox appears in every document. But every document has a TF-IDF score of 0. In the real world, the word fox obviously does not appear in every single web page, but common words like the, a, and appear commonly, so they, as fox in our example, would be filtered out. In summary, TF-IDF boosts rare, meaningful terms and ignores fluff. Google used this algorithm for years, and now so does my engine. So let's talk about it. As said before, I chose Go for the programming language as it is a fast, compiled language with great support for libraries, which I need a few of for this project. Now, any good search engine needs plenty of data for ranking the web pages, so thus I needed to start scraping. Simply means extracting data from websites, which is very simple for computers to do using the HTTP protocol, the same your browser uses to watch this video right now. To scrape responsibly and legally, we need to know if we are even allowed to scrape a page. Luckily, there is a convention that most websites follow, where if you go to any site and type /robots.txt just after the domain, you get this text document. It simply states which pages a robot, such as the scraper in question, is allowed to access. Now we just fetch the robots.txt, parse it, and make the note of the list of pages we are allowed to visit. The code for that looks like this. Here we fetch the domain, either from cache or the database. Here we extract the protocol, HTTP or HTTPS, from the just fetched data. Here we fetch the aforementioned robots.txt using the appropriate protocol. Here, if we failed, we say that we failed. Then we read the robots.txt. Here, if we failed, we say that we failed. Now we go through the file line by line. And if the line starts with user agent, meaning that robots.txt is beginning to describe a user agent, which is a way of identifying an agent in the HTTP protocol. And if the user agent we are describing is asterisk, meaning every there is, we search for this line, disallow. We append the disallowed path to the result, and here we return it with no error. Simple, right? Let's talk a little bit about how I structured the data for, as I will talk about in a minute, millions of sites, so that the searching is still blazing fast. I used SQL, Structured Query Language, namely its instance called PostgreSQL, inside of which I created 5 tables to store all the data I need. The first table is called domains. For every domain I scrape, it holds its ID for speed and space efficiency, its name, and whether or not it supports HTTPS. Then there is the pages table, which for every page stores the page's ID for same reasons as before, the ID of the domain it is linked to, the title, the path, and the time of the scrape. Then is the stems table, but we'll talk about it later. Then is the terms table, which holds the ID of a term, the term itself, its document frequency, and the cached IDF. And lastly, there is the page terms table, which doesn't have an ID. But why? Because it has two IDs. Page ID and term ID that uniquely identify an entry in this table. Then there is a term frequency field, the actual value of the table at a given point, and cached TF-IDF. Let's talk about this one for a sec. Since in SQL there isn't a simple way to create a two-dimensional table, this is how I did it. As you can see, we have two axes, an X and a Y. Going left to right, the X increases, and going top to bottom, the Y increases. But that table could be implemented using a 3-column table. Take any field, like this 7 for example. Since X is equal to 1 and Y is equal to 1, let's note that in another table. And put 7 as the value in another column. Doing that for every value in the table, we get a transformed table that shows the same data. Now, in my project, the x-axis is the pages, and the y-axis is the terms, and the value is the calculated TF-IDF. So technically, the table I have shown before is equivalent to a two-dimensional table that shows page term relevancy. Having the data structure out of the way, let's talk data acquirement. Now, we can legally scrape every website and have the database schema necessary to start scraping. But how do we know which websites to scrape? I figured if I just take the list of some top websites and just scrape them, I will be golden. Just as golden is the drive I will store the data on, the WD Gold 4TB HDD. So I got a list of top 1 million websites, ranked by how often they are visited, from majestic.com, link in the description, and used it for the project. How? For every website in the file, we call the scrape domain function that makes sure the website is registered, either exists in the database, or we scrape it to see if it supports HTTPS. Then we call a recursive function scrape URL on the domain with the root path and recursion depth equal to 0. Inside scrape URL, we check the recursion limit and cache not scrape too much nor too deep. We proceed to checking if the path we are scraping is not disallowed by robots.txt. Read the page's text and tokenize it, insert a new entry to the pages table in the database, stamp all the words and insert each and every one of them into the terms table, then we repeat the process for every link on the site as long as it still links to the same domain. Believe me or not, that's it! With this simple process, I have created a working search engine. Let's try and look at the results. Oh, we have not created the page for it. So... Using Go's built-in net HTTP library, we host a web server with a site with a single search box. If the request path contains the query parameter, we search for it using the search database function, which works as following. It takes the query, tokenizes and stamps it, then does a simple query to the database to deliver us the most relevant sites ranked by relevancy. Then, using Go's built-in HTML template library, we will create a template for each site and bake it into one huge HTML document and send it to the user, which results in... Google's strength is scale, but that's also its weakness. My engine doesn't have to load 50 trackers, inject ads before every result, run 10 machine learning models before showing a link. It just finds what you asked for, just like Google used to. So how does it compare? Look at these instant results, ranked purely by relevance, and look how stupidly fast it is compared to Google. But wait, it can be even faster. Now that is speed. One question arises. Can this actually replace Google? Obviously no. Google handles billions of queries with insane infrastructure. But this proves something important. Sometimes simpler is better. Maybe we don't need AI for everything. Maybe we just need a faster, cleaner way to search. If you want to try it yourself, the code's on my GitHub, and the live demo will be available to all of you on search.jdsecv.xyz. Thank you all so much for watching. Till next time, bye!